It's Michael Kosterlitz. He was born 1943 in Aberdeen, United Kingdom, and he graduated with his PhD from Oxford University in '69, and he is presently the Harrison Farnsworth Professor of Physics at Brown University in the United States. And I know that he has Nordic connections. He visits Sweden, and he has also a close connection to Physics Institute in Finland. So Professor Kosterlitz has given many crucial contributions to the theory of phase transitions. I should mention in particular the Kosterlitz renormalization group equations that have been very influential in many areas of physics, not only the phase transitions in two-dimensional materials that we will hear about, but also, as was alluded to in the lecture by Professor Haldane, that there is a very deep and intriguing connection between classical physics in two dimensions and quantum mechanics in one dimension. And the Kosterlitz renormalization group equations and the Kosterlitz-Thouless phase transition has been instrumental for understanding also quantum properties of matter. Professor Kosterlitz has been awarded the Lars Onsager Prize and the Maxwell Medal, and he will now give the second 2016 Nobel lecture in physics with the title Topological Defects and Phase Transitions. Please, Professor Kosterlitz.
Thank you very much. Oops. Okay. Good morning. It feels a bit strange to be standing here addressing this august audience because I never thought that I would ever end up in this position. But here I am, so I will do my best to try to explain how I got to this point, or at least tell you some of the story how I got here, and in particular pay homage to the man who really started me off in this field, David Thouless. Now, okay, let's see if I can get my computer to work. Okay, so the early work of David, which was very influential to our thinking in this field, he did in a very short physical review paper back in 1969. And it was incredibly short, just 2 sides of a piece of paper, if I remember rightly. And it was basically related to a simple model. It was just a one-dimensional magnetic Ising magnet with a Hamiltonian written up there in the first line, and it depended on, with different ranges, interaction ranges. Okay, so it was known that if the interaction range was longer than 1 over the square of the distance between spins, that there was no magnetization at any temperature and no phase transition. However, if the interaction range was longer, it was also known that there was a transition at finite temperature. It was a transition to a state of finite magnetization. David was asked, he visited Bell Labs, and he was asked, did he know anything about this intermediate situation of where the interaction range was exactly 1 over the distance squared between spins, because this was a strange situation, and nobody really understood what was going on there. And so, according to the story I hear, is that on the way back on the train from Bell Labs to Stony Brook, he had an inspiration. And typical of David's inspiration, actually rather simple, but extremely deep. And now this is the fascinating thing about David Thal, is that his ideas sound quite simple, but when you sort of think about the consequences, or the implications of what he says, you realize, wow, this guy really is deep. He's a very, very deep thinker. So you should never mistake the simplicity of the ideas with the depth, because it's often very simple ideas which are the deepest. Now, so what David simply said was very simple. Let's think about the system and imagine that it's at low temperature, so it's magnetized. And let's assume some magnetization. We're talking about a ferromagnet, so it's simple, no antiferromagnets, no difficulties. And, oh, by the way, I should mention that I am talking in purely classical, about purely classical systems. And the reason for this is that at the time when I got interested in condensed matter, I knew essentially nothing about the subject, and to me, quantum mechanics was just an unnecessary complication which only half understood anyway. So everything I'm going to talk about from now on is purely classical. So to come back to the problem, David said, all right, let's imagine having the system, a magnetized system. Now let's simply imagine flipping a segment of this chain of spins, just reversing the spins. Instead of call the possible values of the spins +1 or -1, and every time you see a +1 spin in this block, change it to -1 and vice versa. So if you do this, the energy change is given by this little formula at the bottom of the slide. So now the consequence of this is just that in this special case of one over distance squared interactions, is that the change in energy is given by a very simple formula. It's basically twice the square root of the magnetization, mu is the magnetization here, times the exchange constant, times the logarithm of the size of the block you've decided to flip. Fine. So then you ask yourself, so what? What is the consequence of this? Well, as you probably know, we're in statistical mechanics, which is what we're trying to do here. The essential quantity that's of interest is the so-called free energy, which is just energy minus temperature times the entropy. And the entropy is nothing other than the logarithm of the number of possibilities. And the number of possibilities is simply related to the number of positions, of allowed positions of the reversal. And the number of allowed positions is basically n, the length of the block. So the change in the free energy is just energy minus temperature times the log times the entropy, and entropy is sort of Boltzmann's constant, this K sub b, which you have to put in to get the dimensions right. And so you get this little formula written down there. Now, the consequence of this is if there is long-range order, in other words, if it's magnetized, then we must have the coefficient of the logarithm of the size of the block must be positive. In other words, we're talking about low temperatures, so the first term must be larger than the second term in the bracket. And then we expect that assuming that does undergo a phase transition, so that some critical temperature called T sub c, that the magnetization disappears. And what has to happen is this free energy difference, this delta F, has to go to 0. Therefore, the critical temperature must be given by the vanishing of the coefficient of the logarithm of the system size. So we've got a formula that twice 2 mu squared J must be equal to KTC at the critical temperature. And remember, the magnetization, mu is the magnetization. Okay, now that formula, which looks sort of very trivial, very obvious, has a remarkable implications. It means the magnetization must go discontinuously to 0 at the critical temperature, assuming, of course, the critical temperature is positive. So, now there was a lot of knowledge and lore about phase transitions available at the time, and what the sort of lore was saying that at a continuous phase transition, the magnetization should disappear smoothly as you approach the critical temperature from below. Okay? Now, assuming this is a continuous transition, this is saying, wait a minute, this formula is saying, wait a minute. No, that can't happen because the magnetization has got to jump discontinuously to 0 as you pass through the critical temperature. This is actually a very strange result, but because normally one thinks of a phase transition where something jumps discontinuously to 0 is what is called a first-order transition. But this transition is well known not to be first order. So this is a most unusual situation. Again, that's very typical of David. He comes up with these apparently very simple arguments which have the most extraordinary consequences. Trouble is that there's no way to argue that this argument is incorrect. So he's now found something unusual again, because he's found a very, very strange situation where we have a system where we have a so-called continuous transition, but it has a discontinuous magnetization at the critical temperature. So this is just the sort of argument which David Fowler's produced, which has some extraordinary, at the time, consequences. It's certainly a correct argument, but what's more important from my point of view was in the work that David and I did together later, and I did myself, this argument, or this observation, was actually extremely influential. Now, let me now tell you a very short story about how I ended up at Birmingham University. I was actually brought up as a high-energy physicist, and so I was really keen on doing the glamorous high-energy physics stuff. And I happened to be at a postdoc in Italy at Torino University, with the ambition of going on to the standard place for high-energy physics afterwards, CERN at Geneva. But as is my standard downfall, I failed to get my paperwork in on time. So I could not get a spot at CERN, and ended up sort of jobless. So I quickly sent my wife, or my girlfriend at the time, down to the railway station in Torino to buy an English newspaper where I could look for some job adverts and apply for whatever job I could find. So I wrote out a few applications, sent them in, and then got offered a job as a long-term postdoc at Birmingham University, which was, to tell the truth, the last place I wanted to go to, because I was determined to go to CERN in Geneva, but it wasn't to happen. So I ended up in Birmingham, and I did some long, tedious calculations, high-energy physics, for about a year. And I got really, really tired of it because, first of all, I didn't get anywhere. Second, I think, just when I was about to write stuff up, or had written the preprint, I was starting to write up the preprint, then suddenly a paper would arrive at my desk doing exactly what I was doing. And so this happened 2 or 3 times. And it was these calculators were produced by some group in Berkeley. So after the second or third time of this, I realized it wasn't going to work, because here I was on my own, calculating away, doing things, and every time I almost was finished, the preprint arrived at my desk. So I was clearly not in a very strong position here. So in desperation, I went around the department in Birmingham asking, begging people for, if they had a problem that might be tractable, perhaps I could look at it. So eventually I ended up in David Fowler's office. And I listened to him talking about introducing to all sorts of weird and wonderful new concepts, things like vortices in superfluid helium films, and phase transitions in 2 dimensions. Of course, much of this was a mystery to me, because I actually had skipped statistical mechanics in graduate school because it didn't seem to be relevant to my proposed field of high-energy physics, which was a mistake. And also, as I say, I was in a place which was the last place I wanted to go to, listening to David explaining lots of weird and wonderful ideas to me, which I could barely understand. However, what David was saying sort of made a lot of intuitive sense to me. So I thought, well, maybe this statistical mechanics stuff, it could be quite interesting. So we started looking at some of these 2-dimensional systems. And the situation in the early 70s is basically summarized on this slide here. And there's a class of models which are basically cover all of the classical statistical models, and they're described by a Hamiltonian given up at the top of the slide there, where we considering a ferromagnetic model in 2 dimensions now, not 3, where we have got n spins of n components, and we keep the spin length fixed at 1, say. And so what was known about these models at the time? Well, not much was solved. The only solved model was the n equals 1 case spin up or down, otherwise known as the 2-dimensional Ising model. Now, this was solved by most extraordinary calculation by Lars Onsager back in, when was it? In the 1940s. And in this model, yes, there is a phase transition, because we know that from the exact solution. The next case is 2-component spins. Now, this was interesting for physical reasons, because this would describe a model. It's a model for a thin film of superfluid helium-4. And what was known about this model at the time was, well, maybe there's a transition there. It might be, but who knows? If the number of spin components is greater than 2, then the simulations, high temperature series expansions, etc., said probably there isn't a phase transition at any finite temperature. And the only thing that was really properly known is the limit of the infinite number of spin components, otherwise known as the spherical model. And an exact solution says this one in 2 dimensions has got no transitions. So clearly this situation needed a bit of further study, particularly because of the importance of the 2-component model, which could be a description of superfluid helium films. Now, there was a piece of experimental evidence floating around, and I show this picture here. It was in a Physical letter 1972, and this piece of evidence, this piece of experimental evidence tells us basically unambiguously that the n equals 2 case does have a phase transition, because you see, this is an experiment done by Marvin Chester and co-workers, and it consisted of looking at the resonant frequency of a vibrating crystal. And they absorbed some helium onto the surface of the crystal and measured the change in the resonant frequency. Now, as you all should know, the resonant frequency of some vibrating object is inversely proportional to the mass. Because the mass increases, the resonant frequency decreases. That's all you need to know at this stage. And so they did a set of experiments. And the dots are the experimental results. The straight line is what you expect, assuming that all the adsorbed helium sticks to the surface, because the film is so thin that any atom of helium that gets absorbed on the surface of the crystal, assuming that it's a normal, forms a normal fluid like water or something, that would, as the crystal moves backwards and forwards, the adsorbed molecules also move backwards and forwards, and therefore will increase the mass of the oscillating object. And so one would expect that as you put more and more fluid on, and the horizontal axis here is just it's basically a formula which tells you, where it gives you an exact measure of the total mass adsorbed onto the surface of the crystal. And so the initial data, when the first few molecules go in, follows the expected straight line. You can see that. But then, at some point, as you absorb more and more helium onto this crystal, something very strange happens. Suddenly, there's a whole mass of adsorbed helium suddenly doesn't contribute to the resonant frequency. And so one can argue that the deviation of the difference between the experimental points and the straight line is a measure of the amount of superfluid, amount of fluid that has decoupled from the crystal. And so once it's decoupled from the crystal, what do? You wave your hands and call it a superfluid, because it is completely unexpected. Okay, so this piece of experimental evidence was staring us in the face, saying that, look, in this system, spin XY system, or planar rotor spin system, there must, in 2 dimensions, there must be a phase transition. Now, suddenly, it does have a transition, which contradicts the standard interpretation at the time of some rigorous theorems, which said that there is no long-range order in such two-dimensional systems. And of course, this rigorous theorem, for many years, no arguing with the rigorous theorem, absolutely correct. But the interpretation could be argued with, because the interpretation of this theorem would say there's no phase transition, because of the standard Landau interpretation that a phase transition implies that suddenly in the ordered phase you have long-range order. So here is a situation where there's clearly a phase transition, but there's a rigorous theorem that also says, okay, there's no long-range order. So the problem that we were then faced with is to somehow reconcile these two apparently contradictory statements. Clearly, the experiment says, look, there is a phase transition. There's the data. It's obvious. There's a phase transition. Okay, that's experimental side. The theoretical side said there's no long-range order. There's no arguing with the theorem, but so the only conclusion one can come to is that the theorem is correct, but it's not relevant. So it's certainly a phase transition. Now, this is typical David Fowler's problem. He could see that there was a contradiction here that can be, should be looked at. My own take on the matter at the time was, I don't understand this, so what? Because I didn't know about these rigorous theorems and so on, but it looked like an interesting problem to work on. So I thought, okay, why not? So we started looking at it. Now, this slide, sorry it looks so busy, but I thought that I would redraw this thing to make it less busy, but of course the Nobel week is so every moment of every day is scheduled for the laureates that there was no time to do anything. So I apologize for this overly busy slide. Now, so what do we know about? What's the situation? The first thing is we're talking about superfluid helium, or if you like, a spin model where two-component spin model where, let's say, assume that the length of the spin is fixed, so the spin configuration can be defined by this angle theta. And if you like, the superfluid order parameter is just the S sub x plus I times S sub y, which can be written in the form amplitude times e to the I theta, where theta is a phase. Now, this whole system is invariant under the phase shifted by any multiple of 2 pi. So, therefore, we can say that the global excitations of this system, or the so-called topological excitations, are what are called vortices. And this is just a spin configuration where if you walk around a contour, some closed contour, then the change in the phase as you go around this closed contour is a multiple of 2 pi. And of course, it has to be a multiple of 2 pi because the order parameter itself has to be the same when you come, if you start somewhere, go around and come back, the system had better be the same thing that you started with. And so this order parameter, which I write as amplitude times e to the I theta, that has to be single valued. And so, therefore, the change of phase as you go round a contour, come back to where you started, must be a multiple of 2 pi, because that leaves the the order parameter itself invariant. However, if the change of phase as you go around some contour is 1 or 2 or -1 or -2, what that's saying is there must be a singularity in the order parameter. Right somewhere inside this contour. And of course, this sounds a little bit unphysical, because after all, what we're talking about here is a film of helium absorbed on some nice continuous surface. So how on earth can something be discontinuous? How on earth can we have a change of, a phase change of 2 pi when we just walk around a circle? Well, it's very simple. We say that, okay, we have got a vortex. What we've done is we've walked around a vortex. Say we've gone round, say, clockwise, and we're changing the phase by 2 pi when we walk around some point in the middle, and then we can say the point in the middle, the blue blob in the middle, is the core of the vortex. And so what happens at the vortex core is, let's say, the magnitude of the order parameter, or just as either, it's just 0. So in other words, if you like, it's a hole. It's like topologically, it's like a hole in the surface. So of course, one can have a contour running around a hole where the phase change can be 2 pi. There's nothing wrong with that. Now, see if I can go back. Okay, now let's go back a little bit and ask, what are the consequences of this? Well, suppose we just make the argument, let's consider a large system, and let's consider an isolated vortex. Just put an isolated vortex in the system. And let's calculate the energy. Okay, the system size it's an L by L system. The energy of an isolated vortex in this system is just proportional to the logarithm of the system size. It's log L over A, where A is some microscopic cutoff, like a lattice spacing or the vortex core size, something like that. The entropy change, or the entropy associated with this vortex, is simply Boltzmann's constant, to get dimensions right, times the logarithm of the number of possible positions of the vortex core. And of course, the number of possible positions is just the total area of the system divided by the area of a vortex core, because that's the number of possible places you can put the vortex. And so you then get that the free energy is E minus the temperature times the entropy. So again, you get this logarithm, this logarithmic formula, a little bit like what we have in the one-dimensional 1 over r squared Ising model. And so you can then just say, okay, the central quantity in statistical mechanics is the free energy. So the associated free energy is just E minus temperature of the entropy. So there's your two formulas for the energy and the entropy. So you just plug that in. And then you can say the probability of such a configuration, or if you like, of having a vortex, this is statistical mechanics again, so I assume you have to know something about statistical mechanics, and it's just proportional to the exponential of I've written beta. By beta, I mean 1 over Boltzmann's constant times temperature, e to the minus beta f, and you have a formula for the free energy. And so the probability of a vortex is the system size divided by the microscopic cutoff, like the core diameter or something like that, to the power of minus pi k minus 2, where k is just the exchange constant divided by Boltzmann's constant times temperature. So in other words, K is a temperature-dependent quantity which is large at low temperatures and small at high temperatures. And so this little formula here, that the probability of having a vortex, an isolated vortex in the system, is L over A, where so L over A is a huge number, to the power of pi k minus 2, where K is a quantity that is inverse in the temperature. So in other words, this probability of a vortex being present is 0 if pi k is greater than 2, as long as the power is negative. That means at low temperatures, the probability of having a vortex is 0. And at higher temperatures, this probability, when pi k is less than 2, this probability has to be 1. Okay, of course, I've forgotten about other normalization of that formula and so on, but let's forget about these little details here. So in other words, this system should have a transition around the temperature such that this factor, this K, which is temperature measure, is a measure of the temperature, is larger than 2 over pi. Now, that is the essential argument of our original paper, which was published way back when in 1972, 73. And we can say that when this temperature-dependent coupling constant K is large, the topological sector, in other words, the number of vortices, because the probability of thermally creating a vortex is 0 at high temperatures, then you can say this single topological sector, the number of vortices won't change because there's a huge energy barrier to get over. It has to be stable. Whereas when the temperature is high, or alternatively this temperature-dependent parameter K is small, then there can be transitions between different topological sectors. And of course, what this in turn means is that, in principle, at low temperatures, you should have a superfluid, but at high temperatures, you won't. Simply because, so let's see why that should happen. Okay, now, let's think about a superfluid. For a moment, what is a superfluid? Let's suppose that the superfluid lives between those two vertical bluish lines. I'm sorry, these slides are not that good. It's because I had to make them all myself, and I'm not the greatest artist. I have to use whatever is available in the little program, so this is the best I could do. Now, in a superfluid, this is a system line between those two vertical lines. Let's suppose we have got a system where we've got a uniform flow in a downward direction at velocity u sub s. That's the superfluid velocity. How can this decay? Because if this flow cannot be dissipated, then we have a superfluid. If it can be dissipated, it's a normal fluid. And the only possible way of doing this, of dissipating the superfluid flow, is to create a vortex-anti-vortex pair and see if they just simply drift further and further apart. And if they can get infinitely far apart, if you like, they go to the system edges and disappear, poof. And in this process, they will unwind the phase and reduce the superfluid velocity slightly. So this is the central question. Now, if you're at high temperatures, these vortices can be produced, appear spontaneously and in large numbers. So this process will easily occur because this superfluid flow would simply cause the vortices to disappear to the sides, and the superfluid velocity would go to 0. All right, so what does this mean? This means that the fluid is normal. Because remember, equilibrium statistical mechanics is always talking about, if you like, the infinite time limit. So it doesn't care what happens at short times. Short times is any mathematical time less than infinity. It doesn't matter if things take longer than the age of the universe to happen, but in equilibrium statistical mechanics, doesn't really care about timescales. So at high temperatures, because of the possibility of creating these vortices, clearly any superfluid flow has to be dissipated by this mechanism I just talked about. At low temperatures, on the other hand, the probability of getting an isolated free vortex, which can drift under the influence of a uniform superfluid velocity, they don't exist, and therefore you have to call that a superfluid. This flow will be at least metastable. So at least now we've got a mechanism for distinguishing between a superfluid and a normal fluid. And so therefore, the next thing we had to study was a system of vortices, which is, you may say to yourself, all right, I could, of course, give you the formula for the energy of some collection of vortices and say we do the statistical mechanics of this. But that formula is so disgustingly complicated, and it's probably longer than I could write down in this PowerPoint slide, so I won't even attempt to do it. But it can be done. However, now David and I cooked up a theory which involved, remember, now here we've got a set of point vortices which interact logarithmically. Now, for those of you who have actually done electrodynamics in arbitrary dimensions, you'll immediately recognize this logarithm as a Coulomb interaction between charges. So one could regard the vortices as a set of point charges interacting with the Coulomb interaction. And so then, of course, once you've got this, you immediately think, dielectric functions, et cetera, et cetera, et cetera. And so one could think of the system in terms of an electrostatic theory. And this is basically what David and I did, or at least rather, let's say, David and I did, back in 1972-73, and that paper is probably the most cited paper either of us have ever written, and it is basically correct, but in our calculations we unfortunately made an incorrect and unfortunately unnecessary simplification which messed everything up, and that calculation has since been straightened out, in 1979 or so, by Peter Young, who basically redid our calculation in a correct manner and pointed out the error that we had made. But also, I was bothered about the results of our calculation because the results didn't look right. I mean, just had a bad feeling about them. So I thought, okay, maybe I should try to do a proper calculation here and use this thing which was just appearing called the renormalization group. Of course, I actually learned the renormalization group from a paper which David had kindly given me by Phil Anderson, Gideon Yuval, and Don Hamann, where they talked about the 1/r² Ising model in the context of the Kondo problem. which was all the rage those days. And I spent about 6 months doing nothing but reading and rereading this paper. So we've got 0 minutes left. Okay, so eventually we got some results. So here are the results of my renormalization group calculation. Now, what this calculation says is that it actually makes some predictions. And what it makes a prediction of is the superfluid density at just below Tc as a function of the critical temperature. And what is interesting about this little curve, this little diagram, is that the theoretical curve is that straight line, which is the theoretical prediction. The various dots are experiments. And according to John Reppy, apparently the dots were all plotted without knowledge of the theory. And then when they learned about the theory, they put the straight line in, and to their great astonishment, it went basically right through the experimental dots. And so one could regard this as an excellent confirmation of the theory. So, and this is basically the reason why our theory has become quite well known, because it actually works and has been measured and verified in many systems. Not, of course, by me. I wish I had done it, but so I better stop there and thank, in particular, the Nobel Committee for awarding us the prize, and my wife and children for putting up with me. Thank you.
So thank you very, very much for this inspiring lecture, and in particular, I hope that all graduate students in the audience listened, so they might think a little bit what is interesting and not interesting, and what is useful and what is not useful in your further studies. And now I will ask all the 3 laureates to come up on the scene, please. Just keep it. And